Thank you for attending this Zoom webinar from around the globe. Before getting started, I just want to remind everyone that the session is being recorded and will be put up on the website. My name is Kyoko Yoshinaga, and I'm the non-resident senior fellow at the Georgetown Institute for Technology, Law, and Policy. I'm very pleased to welcome you to this series on AI governance, co-hosted by the Georgetown Institute for Technology, Law, and Policy and the Yale Information Society Project, Yale ISP. It is also co-sponsored by the Georgetown Global Tech Networking Group, which is made up of international academics and experts who specialize in technology, law, and policy research, led by Professor Anupam Chander. This is a continuation of last spring's AI governance series, and today is our first event this fall. Today's panel is on AI classification frameworks and AI accidents. We'll be joined by two experts in this area from the Georgetown Center for Security and Emerging Technology, and our moderator today is April Falcon Doss, who is the Executive Director of the Georgetown Institute for Technology, Law, and Policy. She spent over a decade at the National Security Agency, where she was Associate General Counsel for Intelligence Law, and she has recently published a book called Cyber Privacy: Who Has Your Data and Why You Should Care. With that, April, the virtual floor is yours.
Kyoko, thank you so much for those opening remarks and introduction, and welcome everyone. I am so pleased to be able to offer this conversation around AI classification frameworks, AI accidents, and AI risks. When we talk about artificial intelligence, one of the challenges I think is that it is a phrase that is used by many people in many different ways to cover lots of different kinds of uses. And so this conversation today about classification frameworks gets to the heart of how to think in a systematic and sensible way about different types of AI and the risks that they pose and what happens when something goes wrong. So I'm thrilled that we have joining us two brilliant researchers. First, we have Catherine Aiken, who is the Director of Data Science and Research at Georgetown's CSET, the Center for Security and Emerging Technology. Catherine was previously CSET survey specialist. She designed and led all of the center's survey and other human subjects research. And before joining CSET, Kat was at the University of Maryland, where she completed her doctorate and taught courses in political science and research methodology. Her research explored non-mainstream political action, and she's conducted research for the International Crisis Behavior Project, Cross-Domain Deterrence Project, and the Johns Hopkins Applied Physics Lab, and taught at the National Consortium for the Study of Terrorism and Responses to Terrorism. Catherine holds a bachelor's from the University of Rochester and a PhD in political science from the University of Maryland. Also joining us is Kat's colleague, Helen Toner. Helen is the Director of Strategy at Georgetown's CSET. She previously worked as a senior research analyst at Open Philanthropy, where she advised policymakers and grant makers on AI policy and strategy. Between working at Open Philanthropy and joining CSET, Helen lived in Beijing, studied the Chinese AI ecosystem as a research affiliate at Oxford University's Center for the Governance of AI. Helen's written for Foreign Affairs and other outlets on the national security implications of AI and machine learning for China and the US. She's testified before the US-China Economic and Security Review Commission. She's a member of the board of directors for OpenAI. Helen holds a master's in security studies from Georgetown, as well as a bachelor's of science in chemical engineering and a diploma in languages from the University of Melbourne. Just a reminder, as you've already heard, this session is being recorded. Please feel free to post questions using the Q&A function. I'll be keeping an eye on those, and we'll tee up those questions either as the hour proceeds or towards the end of the hour after Kat and Helen have walked through sort of the primary chunk of their discussion and presentation. So Kat and Helen, over to you.
Thanks, April, and thanks everyone for joining us. Helen and I are really excited to talk through some of the work we've been doing here at CSET on AI classification frameworks and AI accidents. So before we kind of get into some of the nitty gritty, I wanted to go over a brief overview. So I'm going to begin by talking about how CSET and some of the partners we've worked with for this research view the role of classification and classifying AI systems in the lens of policy and AI governance. And then I'll hand it over to Helen, who will talk about current CSET research and work being done on AI accidents and incidents, and what we can expect from these new or kind of emerging types of accidents and incidents, and how we can take steps to ideally prevent them. Before we go into those specific topics, I just want to give those of you here who might not know much about the Center for Security and Emerging Technology, where Helen and I are doing our research, but we are a data-driven research center who focus on topics. We focus on researching topics at the intersection of security and emerging technology, which, as you can imagine, is a very busy intersection. Our work currently focuses on artificial intelligence as one type of emerging technology. But because artificial intelligence is a very general purpose technology, which Helen will touch on in a bit more detail, there's a wide range of security implications, which can include but aren't limited to supply chains and export controls, immigration and education and workforce pipelines, more traditional defense and military applications, cybersecurity, our alliance structures and diplomacy, and then where we'll be focusing a lot of our talk today, this kind of idea of standards and testing, and how developing standards and testing protocol and procedures is really important for this kind of intersection of technology and security. So that's a very brief overview of what we do. Feel free to check out our website for more, and we'll link to a few of our relevant reports. But with that, I'll hand it over to Helen to give an overview of how we think about AI.
Yeah, so this is just another brief scene setting comment. I'm sure some folks in the audience have been to previous installments in the AI governance series and are very familiar with AI. Maybe other folks are newer to the idea. So I think it's maybe helpful to just say, what do we actually mean? I think artificial intelligence is an incredibly broad term. It doesn't have a clear definition. So I like, talking about it in terms of computers doing smart stuff. So that could refer to all kinds of different approaches to all kinds of different tasks. But in the last, few years, it's really become a topic of increasing interest in Washington, and I'm guessing in New Haven as well. And the big reason why it has suddenly attracted so much more attention is research advances in a particular set of approaches to AI called machine learning, and especially one type of machine learning called deep learning. And the research advances that we've seen kind of starting in the early 2010s have really started to filter through into being used in practice. So this includes, obvious examples like self-driving cars, but also includes things like, Facebook's newsfeed rankings or YouTube's recommendation systems, things like that. So there's a really wide range of uses of these systems, but as they're becoming more widely used and as research is continuing to advance, there's more of a need for sort of policy and governance attention, especially because many of the existing frameworks that we use to think about policy and governance for computers don't necessarily work very well for machine learning and particularly deep learning systems. Okay, so that's all of our setup. I'll now hand back to Kat to talk about classification and come back later to talk about accidents.
Yeah, so here we are into the good stuff, right? So I'm going to provide some overview of work CSET has been doing on AI system classification and some frameworks that we've developed for policymaking and policymakers. And I want to note here quickly that this is a lot of work that CSET's been doing independently, but CSET's also been working with a lot of external partners on this research, most notably the OECD and OECD's network of experts on AI, and specifically the working group on the classification of AI systems. Again, we'll provide some resources at the end of the talk and in the slides if you're more interested in kind of the OECD effort that CSET's been involved in. But I'll provide a brief overview of the work more generally. And this work is really motivated by a fairly obvious problem, and that is the need to monitor and manage AI systems that are being developed and being deployed. And a question that kind of keeps coming up around discussions about this problem and this need is, what aspects of AI systems do we need to know or be able to identify and characterize in order to meet this need and in order to monitor and manage AI systems? So the objective of this work is really to develop a user-friendly framework that allows uniform classification of AI systems along policy-relevant dimensions. So before I go into the actual frameworks and how we developed them, I want to step back to this question of why we classify AI systems. Why does CSET and its partners kind of see classification as a kind of preliminary or foundational first step in AI governance? And that's because AI, as we are kind of hinted at several times, is a general purpose technology. So there's a wide range of AI systems deployed in a wide range of deployment contexts. And we can't necessarily, it's not feasible to take every single AI system and every single deployment context and think about them individually and try to monitor or regulate or govern them independently, right? Each kind of raises unique policy considerations. So instead, it's an important step to be able to kind of characterize the kinds of AI systems and know which of those kinds you are interacting with or operating or monitoring at any given time. And classification is the process by which we can get there. Classification offers clear, kind of concise system level information in a way that is consistent and therefore comparable. So we can kind of take this wide range of systems, this wide range of deployment contexts, and kind of maintain the relevant distinctions based on the context and the system at hand, but while also having the ability to kind of think about them and talk about them uniformly and consistently, and thus compare them. So how did we actually go about developing, kind of working from that baseline of classification as an important first step? How do we develop the frameworks? Well, again, we have this kind of our overarching goal of a framework to classify AI systems to help us navigate the wide range of policy implications of different systems in different deployment contexts. And the discussions came up, we were able to develop kind of a short list of key criteria for what a framework needs to have or needs to look like. And the first of them is that it needs to be usable. It needs to be kind of understandable and usable, but not just by a kind of technical system operator or a kind of system developer. It needs to be usable by a wide range of audiences, whether it's a policymaker or a staffer or a consumer or a user or an operator who doesn't have a robust technical background. So in addition to being usable, a key criteria is that the framework characterizes those elements of a system that are most relevant for policy and governance. And while a lot of different people could have a lot of different ideas about what these core elements are that are most policy relevant, two that really surfaced to the top in kind of more than a year of feedback and discussion were a system's autonomy and its impact. Autonomy, which we'll get more into, but essentially meaning the degree to which the system can produce its output, whether that's a decision, a recommendation, or an actual execute an actual action independent of human involvement. And the system impact, meaning the system directed, the impact of a system directed decision or action on individual and or collective rights or safety. So in addition to being usable and characterizing these elements, a key criteria was that it involves minimal administrative burden, that it doesn't kind of add a huge burden on system developers and or regulators who are using the classification framework to understand the systems that they're developing and that they're deploying. So we wanted to kind of not be too burdensome. And related there is that it should be something that can be built upon for other AI management and governance goals, whether risk assessment, bias mitigation, two very relevant and kind of in progress governance goals that are kind of next steps after a classification. And I want to provide one quick example there. OECD, specifically the working group, has been trying to put this into practice. So the classification framework developed by OECD, we've actually already done some work to be able to link that directly to a risk assessment framework. So you can take a system, put it through the classification, characterize and assign a system to the various framework dimensions, which we'll get into, and then that will automatically assign it to a predefined risk level. So this is a really important criteria, is that the framework can be either modified or expanded to address these additional governance goals. And then finally, a really important criteria for everyone involved was that this be a tested framework. So we wanted, and this is where CSET did kind of the bulk of the work, was to actually develop a study to test the different variations of these frameworks on human users. So we tested amongst nearly 400 human users to result in thousands of unique system classifications, which we were then able to analyze and compare to see how well they reliably produce consistent and accurate system classifications. The last note on the framework development is that we had to have some threshold for which a system registered as an AI system, and therefore a system that needed to be classified using the framework. And so CSET worked with the OECD definition, of an AI system, which is provided here on the slide. And you can go to the full report for more context there. But I want to move on to the actual frameworks that we developed and tested. For the purposes of the presentation, I'm going to call them framework A and B, not the most exciting titles, but easy to talk about and compare that way. And as I might have hinted at, we tested variations of these frameworks. So we actually tested 5 frameworks. And the 2 that we'll talk about here, A and B, had the highest rate of consistent and accurate classifications amongst the human users that use the frameworks. So to briefly overview the 2 frameworks, A, as you can see here, is fairly straightforward. You would take any AI system and you would assign it an autonomy level and an impact level. And you have 3 predefined levels that you can assign a system to. So a system can have either action, decision, or perception autonomy, and it can have either high, medium, or low impact, which results in this kind of 3x3 matrix that's visualized on the slide. And any system would fall into one of these cells. And the idea being that which cell the system falls into provides you really meaningful information to then be able to craft policy or develop governance procedures or protocols based on that system and where it falls in this matrix. We'll go to examples, but first I want to show you framework B and how it compares. Framework B is intentionally a bit more complex and a bit more involved, which comes with some pros and some cons relative to framework A, which we can talk about later if we are interested. But this framework, you would classify a system across 4 core dimensions. The context or the environment in which the system is operating, the input that the system is processing, the model, which is the technical core of the system, and then the output that the system is producing that allows it to actually interact with the context and the environment. And so for each of these 4 core dimensions, you have to know some specific information about the system. So for the context, you need to be able to say the system's industrial sector, that it's the sector that it's deployed in, the system's impact on individual rights and critical functions, and who the intended system user is in that specific deployment context, right, as the system's currently being used or deployed. For input, you would have to be able to characterize the data collection method, so how the system actually collects its input, and also the structure of the data that it is processing. The model is the characterizing how the system acquires its learning capabilities, and then the output is the tasks, plural. You could have more than one that the system is performing, and then the level of autonomy that it has in putting that output into the environment. So you'll see action and autonomy and input within here, but within a much more involved framework. So to take these out of the abstract and maybe make them a bit more concrete, I want to walk through 2 examples of AI systems that have been run through both frameworks. And these 2 systems are very different. So hopefully they allow for some illustration of what you can actually do with these classifications once you have them in hand. And one other quick thing I want to note is both of these examples were included in our testing. And these are two of the highest performing systems in terms of, for both frameworks, human users were able to take only the information provided here on the slide, which is what was provided to our respondents. And they were able to fairly consistently and accurately classify the system using both frameworks. So here we have AlphaGo Zero, which you may or may not be aware of, but is generally a system that plays the board game Go. You may have heard of it because it usually plays Go better than professional human Go players and beats them. And that might be why you've heard of it. But using framework A, remember it's only those 2 dimensions. So with this information about AlphaGo Zero, a human user can identify that it has action autonomy. It can execute an action independent of human involvement. But that action is very low impact in terms of how it affects individual and collective rights and safety. So now we know that this is a high action autonomy, low impact system. But maybe we want a bit more information. We can also use framework B here. We can say that the context in which this system is deployed is arts and entertainment. There's no impact on individual rights, and this isn't performing a critical function. You can then identify the end user, which in this case was an AI expert, but could presumably in other deployment contexts be an amateur Go player. You can characterize the input for the system. The data is collected through human and automated tools, and it is processing complex structured data. And some of this information might not be used that informative when we're only looking at one system, but when we get to our next example, you'll see how that allows for some really meaningful comparisons that are policy relevant. So finally, the model and the output, we can identify that the acquisition, this system acquires its learning capabilities from data and from its experience playing the game, so from system experience as well. And the tasks that it's performing are forecasting and goal-driven optimization. Those are the tasks that it's doing in order to actually make a move in the game. And it has high autonomy, which again, you can see that the impact and the autonomy match framework A, but we are able to have some more information using framework B. So a second example that we can look at is a very different system, a GS missile defense system, which again, you can read the description that we provided to our survey respondents who were tasked with using the framework on the slide. But using just that information, you can identify that this is also an action autonomy system. It can execute an action independent of human involvement, but that action actually has a very high impact. So again, very quickly, you're able to already identify a very meaningful and policy relevant difference between these two systems, but also a similarity in their autonomy level. Framework B, you can see that this system is operating in a very different context, right? National defense, its impact is, it could impact fundamental human rights, and it is deployed in a critical sector. Has a different end user. All of that is important information, especially if we think about comparing it to another system like AlphaGo Zero. It has a similar data collection method to AlphaGo Zero, but it is processing very different. It is processing unstructured data in this case. So we can think about what that means for how we might regulate or govern these systems differently. It acquires its learning capabilities from data, and it performs different tasks. It performs event detection and recognition, but it has high autonomy. So the goal of those two, one, just to help you make the frameworks a bit more concrete, but also to show what we can do once we have these classifications in hand and how we can make really interesting comparisons about system while still talking about them using common vocabulary. So why do we classify AI systems? What can we do once we have these classifications in hand? We can talk about AI systems using a common vocabulary. That means we can do something like build AI system inventories that are, enterprise-wide or even larger, that are comparable and consistent and uniform. We can then take on additional kind of next governance steps, whether it's developing a complementary risk framework that sits on top of the classification framework, or a bias identification framework to then help mitigate bias in the systems that we're deploying. And generally, having these classifications in hand and classifying AI system allows us to go to kind of find a nice middle ground between this one-size-fits-all approach to AI governance, but also the system-specific approach to AI governance to instead identify kind of specific elements in context, while also being able to aggregate systems in a useful, efficient way. And one other really neat thing that classifying AI systems will allow us to do is analyze and characterize the kinds of systems that are involved in AI incidents and accidents. And I'm sure I don't need to go in much detail to explain why that would be very important for AI governance, right? So with that, I will stop rambling about classifying AI systems, and I will let Helen talk about AI incidents and accidents.
Thank you, Kat. Lovely segue there, very nice. I think obviously there are clear links between the ways that classification are useful and the kinds of needs we have when we think about AI accidents and incidents. So that's going to be, the accidents and incidents piece is going to be the focus of my comments today. And again, the motivation here is this sort of cliche of a tech policy problem, right? That technology moves really fast and policy tends to move slow. It can be difficult to keep up with the changing world. And sorry, slide issues. So that raises a question, which is, if the policy response is going to need a little more time or is not going to be able to be as nimble as your average move fast and break things Silicon Valley company, then it would be really helpful to be able to have some kind of foresight into what kinds of problems might arise, or at a very minimum, having really good ways to notice problems as they do arise. And I think if you're looking with this lens of, are there problems that we can see in advance now or problems that we can start to see happening already, then something that really deserves attention is this idea of AI accidents. So in particular, I would posit that on our current trajectory, looking forward, if we continue kind of deploying AI in the ways that we are so far and expanding it as AI becomes even more widespread, then we are going to run the risks of large-scale AI-driven accidents. So if that's true, what can we know about those kinds of accidents? What can we anticipate? How should we be thinking about shaping policy? I think there are two main sources we can use to try and think about what types of accidents might we see. The first source is looking at non-AI technological accidents, these kind of large-scale disasters. I have a few here on the slide. And there's a few different pretty interesting lessons, I think, that we can learn from the history of large-scale technological accidents. One that really stands out and that was really drilled into us in engineering school as well is this idea that these accidents are never, or almost never, from a single source of failure. It's almost always a real stack of different types of problems and different types of failures that end up leading to disaster. And usually, there's a technological level, there's some kind of part failure, there's a management level, there wasn't a process being carried out properly, there's maybe an operator failure, training steps weren't followed, or someone was on break when they shouldn't have been, or things like that. Normally you have these kind of multiple layered failures that lead to disasters of this kind. And a second thing that tends to be common across these types of disasters is that the problem or these layered issues were usually pretty foreseeable. Usually there's not a kind of out of the blue single problem that no one could have anticipated. Usually it's things that people knew about. It's training protocols that weren't followed because they took a little bit longer and people got sick of it. Or it's maintenance that wasn't completed because the company thought that they could get away with it that year and it would be cheaper to just skip maintaining or replacing that unit. So those are, I think, two pretty consistent lessons across past technological accidents. We actually have a whole paper on AI accidents that we'll link to later that goes into some more of what we can learn about potential AI accidents from the past of other accidents. And a second source of information we can use to think about what kinds of AI accidents we might see is to look at what we already know about the weaknesses and vulnerabilities of the AI systems that we're building today. And there are lots of these. I'm sure you've heard plenty about them. But I want to go over three big types of potential failures that I think are helpful to help us kind of conceptualize the space of what kinds of things can go wrong as we're using machine learning and particularly deep learning systems in an increasing range of settings. So these three ways: robustness failures, specification failures, and assurance or interpretability failures. So robustness is essentially referring to what happens when you have unexpected inputs, or the system is in some setting that it wasn't trained for or wasn't prepared for. This one on the right is one of my favorite AI accidents or incidents of all time, because it's great in so many ways. So basically what's happening here is you have an AI-driven camera that is supposed to be automatically tracking the soccer ball in a game. So, it saves you needing a cameraman. I think it's just a local league game. It's, there's not a lot of money involved. So saving money on a cameraman is a good deal. But what you can see happening over and over again is that on this, side nearest to us, this linesman has a bald head that reflects light in a way that the AI cameraman thinks is similar to a soccer ball. And one thing I love about this incident is no one was hurt, that nothing terrible happened. But there's other things I love as well. So another thing is that this is the kind of mistake that no human would ever make, right? And this is really common across AI incidents and problems, is that because these systems sort of function in a way that is actually really different from how humans think and reason, the kinds of mistakes they make are just totally foreign to us. So you would never have a cameraman being like, oh man, that guy has a shiny pale head. That seems like a soccer ball. Let's go film it. Just wouldn't happen. Another thing that's great about this example is it's not something that you would have ever anticipated or thought to fix, and it's also not something that you can really fix, or that it makes sense to fix by focusing on this specific example. So in theory, you could look at this and say, okay, I guess now that we've seen this happen, we should add some more data of guys with bald heads into the training data so that the AI learns not to follow guys with bald heads. I'm like, sure, that will fix this specific problem. But number one, you would never have thought of that in advance. And number two, that's not a general solution at all. This is just showing the ways that AI systems will fail in unexpected ways. And so we need kind of more comprehensive ways to build them robustly in order to be confident that this kind of thing isn't going to happen. So that's robustness failures. These are really common. Specification failures are also really interesting. And where these derive from is that the way we build AI systems depends on us being able to tell the system what we want it to do in a very kind of clear, specific, explicit way. And this works well when what we want it to do is something pretty simple that it's easy to formulate in a clear and specific way. But usually what we want is actually not that simple. Usually there's kind of nuance that we may not even be aware of. So in this case, what you can see on the right-hand side is a boat. It's a boat in a racing game, and it's supposed to be driving around a larger course. If you actually look at the top left-hand corner of the GIF, you can see the little colored dots moving their way around a larger course. But this AI boat was told by the AI researchers working on it, was told, okay, what you should do is you should get points in this game, because the people training, I think they were training AIs to play a whole lot of different video games, and normally winning points is a good way to get through the level or win the race or whatever. But this boat has found that actually what it can do is careen around a harbor, setting itself on fire, because these little green bonus diamonds or whatever they are keep regenerating, and so it can just sort of get infinite points by repeatedly setting itself on fire. And so this is an example of a broader type of problem where AI just does what we tell it to do. And so that means that if what we tell it to do is not exactly what we want, we may end up with outcomes that are actually not at all what we're looking for. And then a third category of failures or problems is around assurance and interpretability. And so this comes from the fact that AI systems behavior is difficult to predict and also difficult to understand and dig into. So the example I have here is the types of AI systems that are being used for hiring, which I personally find pretty terrifying that this is apparently becoming widespread. There's all kinds of potential issues actually with the use of AI in hiring systems, but the one I wanted to focus on here was these systems are totally incapable of going into any depth on how they are coming to the conclusions that they come to. So, depending on what they are, it might be a resume screening thing, it might be a chatbot that chats with applicants, it might be a video thing. And they usually give you some kind of, breakdown of, oh, this applicant has, relevant experience score out of 10 and, sociability score out of 10 or whatever it might be, which might give you the illusion that you're getting some insight into how the system works. But unlike a human interviewer, we have no way at present, it's not technically possible at present to interrogate any of those questions, to say, oh, you said sociability 5 out of 10, like what was wrong? Why did you say that? What could this candidate improve on to be stronger in that dimension, or things like that? There's one test of a hiring system where apparently a candidate got really high scores for their English skills, but the people testing the system had the person speak entirely in German. So the system just gave really high English scores despite not hearing any English. So, this difficulty of being able to interrogate and say, what's going on here? How is this functioning is a real problem. Okay, so those are 3 types of weaknesses and vulnerabilities that we see and that are likely to contribute to potential accidents and incidents in the future. So putting this all together, trying to understand where are the risks of potential large-scale incidents highest, we've identified 5 factors, again, combining the sort of what we know about past technological accidents and what we know about the weaknesses of current AI systems. The first factor is competitive pressure. So this is essentially, it can be competition between companies, can be competition between research labs or countries or whatever it might be. And this is the idea of, well, we know we're kind of rushed. We know we didn't have time to test the system properly, but our competitors are going out and using their system, so we have to move fast. And this is actually was directly implicated in the Boeing 747 MAX, I think 737 MAX, the plane that had 2 crashes that killed everyone on board. What happened there was that Boeing found out on short notice that Airbus was going to bring out an airplane that Boeing had not known about, and Boeing felt that it needed to put out a competitor and an updated model to compete with that Airbus plane. And so they rushed the process. They moved really quickly. They deliberately tried to sidestep the kinds of testing and pilot training that they would need to do. They sort of worked around the rules in order to be able to move faster. And the result was disaster. So that's competitive pressure. A second factor is system complexity. And this is, again, getting back at this idea of the difficulty of understanding what's going on the inside of these systems, meaning that failures of individual pieces might interact in ways that we don't necessarily understand and that could cause bigger problems. So, if you think on the one hand of a simple system, so, the AI cameraman in the soccer game is an example of a pretty simple system. The AI's job is just to steer the camera. So if something goes wrong with the camera, it's a bummer for the people watching online, but it doesn't affect the soccer players. It doesn't affect the match, it doesn't affect the stadium. It's just the AI steering the camera. That's quite simple. In contrast, you could think about something like embedding AI into the operations of a chemical plant, for instance, or maybe you would have lots of different data coming in from different sensors, steering different flows inside the chemical plant, creating alerts for things that need maintenance or need attention. And there, basically, the more interacting pieces you have, and this has been seen in non-AI incidents as well, the more you have kind of lots of interacting factors that are working together in complex ways, the easier it is to have interacting failures that create really unexpected problems. A third factor is when systems are operating faster than a human can intervene, can understand what's going on and step in to fix it. One example we have here in the real world is the flash crash in 2012, I want to say 2013, which was on the markets when we had high-speed trading bots. They somehow got into some kind of spiral where billions of dollars were lost in a matter of seconds. There was no time to step in. Luckily, because it's a financial market that is all handled digitally, it's possible to have automatic checks and to if necessary, you could restore the market to a previous stage or something like that if something really disastrous happened. So if if something like this happens in a setting where it's easy to turn back the clock, then great. Obviously, if you had a similar failure in the real world and people were injured or property was damaged or what have you, that we don't have that option. A fourth factor is looking at untrained or distracted users. So there's a lot of research at this point showing some of the challenges of humans and machines working together. Some of these challenges include the fact that humans are really inclined to trust machines or trust robots often more than is called for. Often, especially if you have even a tiny bit of experience with a system working well, people will then assume that the system is going to continue working well and that they can trust it without questioning. And then, of course, we also have lots of experience and lots of research at this point on the ways that humans are really bad at monitoring computer systems, really bad at being constantly alert and ready to step in at any moment. And so this has been a real problem, for instance, with autonomous vehicles, of course, where you have these sort of quote unquote autopilot systems that work well most of the time, but need human involvement some of the time. And we've seen repeatedly that humans are often not good enough at jumping in quickly when their attention is needed, because if you're zoning out playing a game on your phone and then your car suddenly needs your attention, you're not going to know what's going on. You're not going to have the situational awareness. And we have seen that cause accidents and crashes. And then the fifth factor, systems with many instances. This is basically saying, because AI tends to be digital, it's very easy for it to be, the same model to be used in many different places. So again, autonomous vehicles are an example of this. Tesla's autopilot software being deployed on many different cars. But it's also true of things like a relevant incident we've seen here involves Alexa, the Amazon smart home thing, where there was one issue where a little girl told Alexa to order her a dollhouse and cookies, and her mom wasn't around, and so this mystery package of a $200 dollhouse showed up on her door, which is by itself kind of just sweet. But then what happened was that story got reported on local news all around the country, and when local news reported on it, they included the sentence, "Alexa, buy me a dollhouse," which meant that in the houses of many people all around the country listening to the local news, their Alexa turned on and ordered them a dollhouse, right? So that's another example of how the fact that you have the same system in many different places means you can get these sort of correlated failures, or the same issue causing problems in many places for many people. Okay, so then what can we do about it? There's a few different options. At the moment, the top one is to be investing in the basic science underlying these failures. So to understand better, why do our AI systems behave this way? How can we fix it? How can we understand when these problems are likely to occur and when they're not likely to occur? So something we can do really well for older generations of systems is give them kind of performance bounds of like, we understand that this system, if it's used in this context, is going to stay within these bounds of performance. And we just really don't have any way of doing that with deep learning systems right now, or of solving these other problems of specification, interpretability, and so on. So basic science funding is an absolute must. A second thing is to be investing in the standards capacity to develop benchmarks and standards for how good do these systems need to be for different contexts, and how we can be testing and evaluating them, assuring them to ensure that if they're going to be used in high stakes contexts, that is a wise decision. And here, certainly a lot of the work that Kat was talking about with classifying systems would be really helpful to understand what kinds of standards and benchmarks do we need to use for what kinds of systems, what kind of tests do we need to run for which kinds of things. Because something like AlphaGo, it really doesn't seem like we need any legal restrictions on what kinds of Go playing bots you need. Maybe Go associations will figure out what is appropriate for their different tournaments, but that the federal government doesn't need to step in there, right? Whereas it's something that's higher impact or that functions differently, that could be much more necessary. Third, working across borders to try and tackle these risks. So this includes working with US allies and partners on developing the kinds of standards or testing frameworks or things like that we need. That's absolutely essential. It also includes potentially working with competitors or adversaries, because these kinds of accidents and incidents are something that could affect, it's in the interests of all sides to try and prevent unintentional disasters or unintentional escalations on the battlefield, things like that. Very much in the same way that nuclear safety and security is in the interest, was in the interest of all parties during the Cold War. I think making sure that we understand and are able to prevent these kinds of AI failures is likely something that we could certainly work with China or Russia or other countries on as well. And then fourth, and this fourth point will feed into a quick demo that I want to do before wrapping up. The fourth is that I think we could use much better ways of sharing and organizing information about the types of accidents and incidents that we are already seeing, because we are already seeing plenty. And what exists already in this space is a privately run, volunteer-run effort by the Partnership on AI, which is a sort of industry consortium type organization. And they have this database, which I believe you are now able to see, called the AI Incident Database at incidentdatabase.ai. And what they're doing here is they're gathering based on media reports, so based on public reporting of AI incidents, they're gathering information on ways that AI is causing problems. So this includes things like YouTube recommending totally inappropriate things to kids because the YouTube algorithm has found out that it will keep kids on the app if it recommends these totally inappropriate things. It also includes issues like facial recognition being used to arrest people and then turning out to be completely wrong and the harms caused by that. There's a whole suite of different incidents that are covered in the database. So if you're interested, I'd encourage you to take a look at that later. But that database is privately run, has to rely on publicly available information. And so it can do some great work in collecting what we know about incidents. But it's very different from what we have in other spaces, in aviation or in cybersecurity and many other sectors, where there are actually government-run efforts to collect information on when incidents happened, why they happened, and what went on behind the scenes. Obviously that often involves getting companies to say more about what happened than they might be comfortable saying publicly, and so on. So there's limits to how much can be done in a sort of in the type of privately run effort that is what we have so far. Okay, so wrapping up. This is this accidents report is the one that I mentioned that goes into some more depth on when we might see accidents and what to do about it. You can head to incidentdatabase.ai to see more about the incidents that have already occurred in practice in the real world. And then this is the work that Kat was discussing with the OECD on classifying AI systems. I believe that is all we have for now. So I'll hand back over to April for Q&A.
Helen and Kat, thank you both so much. And we have a fair handful of questions that have come in both through the chat function and the Q&A function. And one place to start is this question about what governing bodies might adopt or use these frameworks. You've mentioned the OECD framework. You've talked about the possible federal approaches to mandating accident disclosure, something that's down the road a bit, but all these possibilities. So even the Go Games Tournament Association, what kind of governing bodies might adopt or use these frameworks?
Yeah, happy to. I saw that question come in and I started jotting down some of the kind of bodies that we've already been talking to about how this framework might be useful for them. And I think one, there's kind of like the government, right? There's like executive agencies, and we can think here of an agency that might need to be inventorying the system that it's deploying, and then so they can then assess their inventory and be able to identify high impact, high autonomy, low impact, low autonomy systems, or whatever the use case is, or the relevant dimensions that they are interested in tracking are. But so we've actually, part of this has been developed actually in collaboration with DHS. So they are explicitly interested in having some sort of framework to be able to characterize the systems that they are deploying. We've talked with NIST about using this framework to be able to classify systems and then help with bias frameworks that they're developing. So again, varying degrees of kind of compliance, right, with using the framework. But I think there's talk of it both being perhaps a mandatory requirement for understanding the systems that are being developed and deployed. But I think Helen's kind of Go Association illustrates other types of governing bodies that we've talked with a lot of industry associations or professional associations who might want to put forth best practices and say, this framework is a useful step to kind of establish as an industry-wide or kind of sector-wide best practice. And the other thing I want to note is international bodies. So the EU and the European Commission and their AI regulation that has been proposed is pretty closely linked with the development of this framework as well. So pretty high level, but those are some of the governing bodies that we had in mind, were helped motivated this work, but then also have been interested in this work as it's been developed.
So bearing in mind that there's interest at the US federal level, interest among international bodies, and interest amongst in the commercial sector, amongst trade associations and industry, is there any pushback against the idea of exploring classification frameworks? Any controversies here? Any resistance to this concept?
Yeah, great question. I don't know that resistance is the right word. I think the main source of resistance that I've been privy to or heard kind of consistently is the administrative burden part that we talked about in making sure that whether it's on the kind of development side and requiring system developers to, maybe classify every system they're developing or experimenting with or putting to market versus, it being, a low burden for actual administrators or regulators to actually use the framework in practice and on scale. So I think the administrative burden and making sure this isn't hampering, development, but also isn't just additional red tape has been articulated a lot. And the one other thing I want to note in terms of, and this relates to one of the questions in the chat, is that the framework doesn't include enough, or the framework is looking at this, is missing a policy relevant element, which of course is a critique that could stand at any point with any framework, right? So it's been a hard one to kind of find the right balance. But there's been a lot of talk about there needing to be more robust classification. There needs to be a more robust classification in terms of the AI model. What type of model is it? Not just how is it learning, it's acquiring its learning capabilities, but because that's the information you actually need to be able to infer or better understand things like explainability. And that's a bit hard because we're not quite sure yet, and we haven't really found a solution or a viable way to actually get that kind of information about the systems and widely available for anybody using the framework. Or we don't even know if that's a desirable outcome. So that's kind of been a kind of persistent challenge, and I guess the main source of pushback, to kind of answer your question a little more.
Yeah, and a related question, a specific one that came in through the chat is, what's your take regarding the AI taxonomies currently developed within the EU framework? And by this, I presume the poster is referring to the EU's draft AI regulations that would identify, sort of risk categories for AI systems: unacceptable risk systems, high risk systems, limited and minimal risk systems. Those remain draft regulations at this point. Is there an intersection between the EU draft regulations and the OECD work? Is there other kind of synergy or points of departure that you're seeing?
Yeah, I think one thing I wanted to highlight here, because it relates to one of the other questions as well, at least that I saw come in earlier, is that one synergy, if you will, that has been really important in our discussions is actually being able to use the framework to identify systems that are not risky, right, or that are low risk. And so actually in OECD has been working with a different risk kind of taxonomy, and it was developed, I might have this wrong, so please don't quote me, by the German Data Commission. Oh no, I'm going to butcher it, but I can definitely provide this information with the slides. But we were working with a different, a bit more granular risk assessment or risk category level, and our top priority was being able to use the classification framework to identify level 0 risk systems. Because part of this like low administrative burden, like not wanting the framework to hamper development. So what are these systems like AlphaGo 0 that can kind of immediately pass go, pun not intended, right? That we can just immediately identify as level 0 risk, and therefore we don't have to maybe go into some of these more burdensome regulatory requirements or governance tasks. So I don't think that totally answers the question of like our take on this taxonomy, but I think that's one way in which we've been thinking about how they relate to one another and how they can work together.
And I think that ties in with another question we saw in the Q&A, which is from a legal and policy perspective, the poster writes, why do we need a framework that puts AlphaGo and Aegis in the same box? What problem needs to be solved here? And I think what I'm taking from your discussions is that, in fact, they're not in the same box, that a classification framework helps identify what things are low autonomy, low impact, what things are low risk by other kinds of measures. And so that could help drive decisions about what gets regulated and what doesn't. But maybe you can elaborate more on that and this question from the poster in the Q&A.
Yeah, April, that's kind of what I had in mind here, is this idea of one of the needs is, I think there can be a bit of a push to say it is AI, therefore it is risky. And so I think part of this of why you still would maybe want to put something like AlphaGo 0 through the system is because then you have a system, or through the framework, excuse me, is that you have maybe a systematic way to actually say, okay, it is, and it's an AI system and it is highly autonomous, but it also falls in this category, whether you're using framework A and you say, well, it's low impact and therefore maybe it goes into level 0 risk. Or if you use the more involved framework, you can use other categories within that framework to say, okay, it's low risk, it therefore goes in this box, even though, when you're looking only at AI systems, it's in the same box, and then AI systems that are highly autonomous, it's in the same box. But then you can kind of go within that box to actually identify systems based on your kind of the question at hand. So I think that's the need. The other one is really this kind of preliminary need of being able to know what systems are out there, right? Being able to inventory and talk about systems. And so we know what AI systems are out there and which ones kind of fall within the category of needing to be regulated or not, to kind of put it very bluntly.
Yeah, that all makes sense. I know we're almost up to time. I want to make sure we squeeze in one more question, and I apologize to everybody participating that we're not going to be able to get to all of the questions. So Helen, one question came in that said, could Helen briefly introduce the governance for the Chinese AI industry? Do Chinese regulators adopt the frameworks that we've been talking about here?
Yeah, so I think China, like just about everywhere at this point, is doing their own thing. And so far, I don't believe they've introduced anything. I think the EU is the main jurisdiction I'm aware of that has proposed a sort of cross-cutting AI governance model with the proposed regulation that we've been discussing. China so far, more like the US and other countries, has been going a little bit more piecemeal. One thing that they introduced recently that was pretty interesting actually was a draft regulation for recommendation systems, which is a use of AI that is super widespread. AI is being used to recommend YouTube videos, Amazon products. It's, the Facebook ranking your newsfeed and so on is all AI. So that's actually one area where China has been ahead of the rest of the world, is in thinking about how to regulate those uses of AI, of recommendation algorithms. And the draft that they've put out has some kind of clear Chinese sort of information control type elements to it, such as tighter restrictions on companies that might have any element of sort of social organizing or political action. But it also just has some sort of interesting, more broadly applicable regulations around allowing users to see, why things are being targeted to them or how things are being targeted to them, or things like that. They have an interesting thing in there about not allowing products to be designed, or not allowing products to addict users, or to cause users to be engrossed in the product, is the Chinese word, engrossed/addicted. And so I don't know, that some of it is sort of Chinese information control models, but some of it is just really interesting attempts to grapple with the challenges that everyone is dealing with these recommendation systems. And so I'm very interested to see what happens as those regulations start getting implemented, how well they work, what kinds of stumbling blocks they come up against, and so on.
I want to thank you both so much. I know we have run out of time. Again, apologies to folks participating that we weren't able to address all the questions. Helen and Kat, your insights are invaluable. Thank you for providing the links to the resources that you've been talking about. Daniel, I'll turn it over to you for closing remarks.
Thank you, Catherine and Helen from us at the ISP as well. And thank you, April and Kyoko, for running the show. As Kyoko mentioned, we'll have the video and the summary up online in a matter of a few weeks. And thank you for our audience. For those of you interested in the next installment of the joint AI Governance Symposium, it will be on Friday, October 29th at 11 a.m. and it will be on AI and climate change. You are all welcome to join, and see you next time.